All right. So let's talk about chapter 6. I've been saying that every derivative rule is also an integral rule. This is one that we got to work a little bit harder for, though. So this is the first technique in chapter 6. We're in section 6.1. This is called integration by parts. The basic idea is that we're going to take the product rule for derivatives, but we are going to do it backwards to say something useful about integrals instead. So here I've written out the product rule. If I'm taking d dx, derivative operator, of the function f of x times g of x, then it should be somewhat familiar. I get f of x times g prime of x plus f prime of x times g of x. Now, if I want to make this a rule about integrals, instead, I'm taking the derivative of this function on the left, I get this function on the right. So it must be that if I integrate this function on the right, I should get this function on the left, up to a constant. So this would be saying f of x times g of x is equal to the integral of f of x times g prime of x plus f prime of x times g of x, and all of that together inside the integral dx. Well, not a whole lot of integrals come my way that look like that. And that's saying something. I teach calculus. I see a lot of integrals. So if I want this formula to be useful, I'm going to need to rearrange it. I'm going to use a little bit of algebra on this formula. So the first thing I'm going to do is I'm going to split that integral. Anytime I have the integral of two things added together, I can just have the integral of the first thing plus the integral of the second thing. I would say that integrals are linear. But that's still not so great in terms of a tool. That's telling me that this function on the left is equal to the sum of two different integrals. But I want my rule to start out with a hard integral, and I'm going to turn that hard integral into an easier integral. That's the way I like my formulas to work. So I'm going to subtract and put one of these integrals onto one side of that equation, and I'll keep the other of those integrals on the other side of the equation. So for those of you playing along at home, we have now got f of x times g of x minus the integral of f prime of x times g of x dx. All of that business is equal to the integral f of x times g prime of x dx. That is a true statement. Now, this might not be the version that we work with day to day. This is kind of a lot to write down. A lot of x's running around. So usually when we're checking in the backs of formula sheets and things like that, we have an abbreviated way to write this. The same way as my u substitution, I was saying that my du, the differential of u, well, that's really u prime of x times dx, right? That's just shorthand for when I'm changing variables. I'm going to change variables here to make the equation a little bit shorter, but still the same amount of information. Now, the convention the mathematicians like to use is the variables u and v. And that's what I'll be using here just so we can follow along with the book. I'm going to use the letter u to mean the function f of x. And I'm going to use the letter v to mean the function g of x. And just like in my u substitution video, this gives us an exchange rate. A single du is worth this many dx's. What's the conversion rate? F prime of x. A single dv is worth this many dx's. What's my exchange rate? G prime of x. These functions are implied by the functions over here. As soon as I say u equals f of x, it automatically implies this relationship between my dx and my du. And those are the things I need to keep track of as I'm performing calculus manipulations. There's a lot going on here. It's pretty dense in information, but the formula is so much nicer now. The formula says integral of u dv is equal to the product u times v minus the integral of v du. That is our new formula for today. So this video is just about where the formula comes from. You can rewind it to hear me talk through this stuff again. To see it in action, you'll have to check my next video. See you in a bit.